Hi, welcome to week one. This is going to be the first lecture or kind of video for this course that actually kind of gets into the content of the course and what are the things that we're going to need to know. We're going to start by talking about carbon and why carbon is special, and then we're going to move on to how do we classify carbon, and we'll get into just a little bit of introduction into how we're going to organize this kind of first unit, which is all about the structure of organic compounds. Okay, I'm going to switch this over and we will begin. So organic chemistry is the study of carbon, right? And so the first question we should probably ask is why did we choose carbon, right? What makes carbon special and makes it worthy of its whole own subset of chemistry, right? Because organic chemistry is almost entirely focused on carbon. So the answer to why carbon is kind of a twofold answer. The first answer is carbon is stable and unreactive in general. Right? And so carbon is a good compound to make structures because it's not going to react and fall apart and do all these other things, right? And the reasoning behind this is that neutral carbon neutral carbon generally has no lone pairs. Right? And this idea of lone pairs tying into reactivity, that's a really important one for organic chemistry. We're going to talk about that a lot. Okay. The other thing that's important for carbon is that carbon can be structurally complex. Right? Both of these things come from the application of the octet rule. Right? If we look at the octet rule for carbon, carbon has 4 valence electrons. And so in order to satisfy the octet rule, carbon has to kind of make a whole bunch of bonds and share electrons with other atoms that surround it in order to reach that magic number of 8 electrons, right? And so neutral carbon tends to have 4 bonds. So when it's neutral, that usually means 4 bonds, right? Because it has to share and kind of acquire 4 electrons from its neighboring atoms. And that means that we can make these structures structurally complex. If you're making 4 new bonds to each atom, right, you can imagine there's going to be a lot of different kind of possibilities for the ways that we kind of stick those things together. Furthermore, the fact that each valence electron then has to be a part of this bond means that we have no lone pairs. And so the octet rule really kind of sets carbon up to be this stable, unreactive, but still structurally complex compound or structurally complex element that then if you have a bunch of chemicals that are going to stick around that we can study, but also they have all these different structures, this is what makes organic chemistry really interesting. Um, so we have lots, so they're structurally complex, which means we have lots of potential structures. And so the first thing that we're going to learn about in organic chemistry is we're going to look at how do we differentiate between all these structures. So a place to start, the first question that we are going to concern ourselves with in this course is how do we differentiate between all these structures. And organic chemists have 2 ways, right? So there's going to be 2 things that we're going to do. One, we're going to talk about how we draw these structures. And 2, we're going to talk about how we name these structures, right? So we're going to represent organic structures in 2 ways. One way is we're going to draw them, and the other way is that we're going to give them names. And each structure is going to get its own name. And so we have a whole big system for this because there's so many structures. The first type of naming that we're going to talk about is hybridization. So what are the types of carbon? Hybridization is just a fancy word for what are the types of carbon that we are interested in, right? And there are 3 types. So the first type is an sp3 hybridized carbon. sp3 carbon. That is a carbon that has 4 single bonds to it. Right? So this is 4 single bonds. Or alternatively, we call these sigma bonds. We have the Greek letter sigma in there. Sigma bonds and single bonds essentially mean the same thing. All right, so where does sp3 come from? Every carbon has four valence orbitals. Right? This comes from the periodic table. You guys have talked about this in Gen Chem before. We have the s orbital. We have 3 p orbitals, right? So we have 4 total orbitals. If each one of these orbitals is involved in a sigma bond, like this carbon here that has 4 single bonds coming off of it, we just kind of group all of those together and we say that the s and 3p orbitals are all working together. That's an sp3 hybridized carbon. We can also have a case where only 3 of those orbitals are involved in making sigma bonds, so sp2 carbon, and that would look something like this. Now, of course, that's not a carbon with a full octet because it only has 3 bonds to it. It only has 6 electrons surrounding it, and so we're going to make a double bond here to complete the octet. So we have 3 sigma bonds, right? Those were the 3 that I drew first. Single bond here, single bond. Actually, I can label these sigma, sigma, and this was a sigma bond. And then we added one new type of bond, the double bond here, and that one is a pi bond. Right, so every sp2 carbon is always going to have a pi bond. In fact, pi bonds are going to be the way that we identify sp2 carbons. And now this is going to become really important for reactivity and stability as we go forward. So those pi bonds are going to be important. We can also, of course, keep going. An sp carbon is going to be a similar thing where the carbon has 2 sigma bonds. Right? We combine 2 of these orbitals, an s and a p, to make sigma bonds, and then we're going to add 2 pi bonds to this, and I'm going to add them on the same side. A pi bond here, a pi bond here. This is a sigma, this is a sigma, and we have 2 pi bonds. Okay, so if a carbon has 2 pi bonds attached to it, that makes it sp carbon. So the number of pi bonds determines the hybridization, determines the type of carbon that we are going to, how we're going to designate each of these carbons. Right? So we have our list of kind of new vocabulary terms up here. We have sp3, sp2, sp, we have sigma bond and pi bond. All of these are concepts that you may or may not have seen before, but things that are going to be really important that are going to come up over and over again, right? So if we wanted to define a sigma bond specifically here, right? A sigma bond is going to be an attachment to another atom, right? Sigma bonds are the things that attach carbon, or it doesn't have to be carbon, but we're talking about carbon, attachment to another atom, right? So that first bond that connects, I guess I didn't draw all these out as sigma, 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 and sigma, right? The bond that attaches that carbon to something else. And then the pi bond is any additional bond after the first. Right? So we have a sigma bond that connects the atoms, and then we add a pi bond to make a double bond. We have a sigma bond that connects the atoms, and then we add 2 pi bonds to make a triple bond. Right? So anything after that first atom is going to be a pi bond. All right. So this is kind of the first introduction. We have kind of, this is how we're going to name things. We're going to talk about the carbon atom, the different types of carbon atoms, and all that kind of thing. As we go forward in this first unit, the big thing here, the big thing that we're looking at is structure, right? Everything that we talk about in these first 4 or 5 weeks is going to be structure. Unit 1, if we had a name for it, Unit 1 would be structure. And I said that organic chemists have kind of 2 ways of thinking about structure. We have naming and we have drawing. Right? And so we talked a little bit about naming here. We talked about hybridization and all of that. Where we're going to go over the next couple of videos is we're going to really dig into this constitutional isomers, whoops, right, side of things, which is kind of the interface between naming and drawing, right? So when we if we can get a really good handle on constitutional isomers and how to name them and how to draw them, then that will make sense for a lot of this other stuff. As we get further into in weeks 2 and 3 and 4 and stuff, we'll get into drawing resonance structures, right? We'll get into drawing conformational isomers, and we'll get into naming stereoisomers and all of that kind of stuff going forward. But for now, for the first week or so, we're going to be focused in this area right here, the kind of the interface between naming and drawing. All right, so where we're going next, we're going to talk about formal charge and degrees of unsaturation and all that other fun stuff in the next video. I hope that you join me for that, and we'll see you soon.